Hello everyone, today we're going to learn how to model with exponential equations. And basically guys, there are two major problems which can be solved using exponential equation. Problem number one is population growth. Population growth happens when you have some natural population, which can be people, bacteria, cats, anything which grow producing offsprings. Normally guys, we understand that, for example, you have a village of people, right? And there are maybe like 20 people there, and they can have, well, every two can have one kid a year, right? And you understand that if the village is twice bigger, they're going to have 2 times more kids. So population problem appear when increase in population, which is like kids, is proportional to population itself. Well, you understand, more population you have, more kids you are going to have. Well, unless there are some reasons to not have it, like some restrictions. So population growth. Our first problem is population growth, and usually population growth is described by exponential model. Exponential model for population growth looks next way. N population at moment time of t is equal initial population n0 e to the power of rt. So what is what here? n0 initial population. Well, can be population at a certain time. T is time, and r is relative rate of growth. You guys probably remember that we've seen a similar equation when we were doing continuously compounded interest. Let me write down R better. That's the same equation actually. So actually money are using this equation. So money grow exponentially if you continuously compound interest. Okay, so guys, what this equation usually helps to solve. For example, a typical problem is bacteria growth. Imagine that we have a culture problem. Imagine that we have a culture with initial population of bacteria, like, I don't know, 500 bacteria. And a relative rate of growth, R, is equal 0.4. We're going to talk a little bit like what it's going to define actually. And that's 0.4. We're going to usually, like, you need to know for which time it grows 0.4. 0.44 is here per hour. And the question is when the count of bacteria N is going to be 80,000. Okay, so how do we solve problems like this? First, we write down the equation N of T, number of bacteria depending on time. And we are just going to plug in N0, which is 500 initial bacteria population. The rate of growth is 0.4. In our money problem, that's a percentage rate, right? And T is going to be here just as a variable. Now, what is given? Given is that eventually, after a certain time of T is going to be 80,000 of bacteria. So we're going to write down 80,000 equals 500 e to the power of 0.4 by t. If you look at this, you can recognize what? Exponential equation. To solve this exponential equation, we'll need to first separate exponential function. Right now it has a coefficient. I'm going to divide by 500 both sides and eliminate this coefficient. Here it cancels, and here I'm going to get 2 to cancel. 8 divided over 5 is like 16, so I'm going to have 160 equals e to the power of 0.4t. Now I can apply ln on both sides, like I usually do when I solve exponential equation, right? I'm going to put ln here and ln here. Ln here is just going to give me ln of 160. Ln here is going to be canceled with exponential function because of cancellation equation and give me 0.4t. Now I can find t dividing by 0.4, right? Ln of 160 divided by 0.4. And if you plug everything into calculator, you can figure out that t is going to be approximately equal 12.7. The question is, what are the units in time? Like, is it minute, seconds, years, days? Well, because population growth was given the rate per hour, we're going to get here hours. 12.7 hours. After 12.7 hours, we are going to have like 8,000 bacteria. Well, you see bacteria grows very rapidly, right? Just like half a day, and you have like 80,000. So guys, what the rate of growth defining over here? You see, you remember that exponential function usually kind of grows very rapidly, right? Actually, this number, if you make it bigger, it's going to grow even faster. So this number defines how fast actually culture is growing. So are you going to have like 80,000 bacteria in 12 hours or in maybe 1 hour? It depends on the rate of growth. Greater rate is going to produce more bacteria sooner. Okay. Now, our second typical problem is called radioactive decay. What is radioactive decay? Well, you know that there are some radioactive materials, right? What happens to radioactive materials? Well, they are not stable. So not stable means that eventually they split in two parts. So imagine that was nucleus of one material, and eventually it splits into two smaller ones, and there's some energy going away also. This is called, the process is called spontaneous radioactive decay. Fortunately or not, spontaneous radioactive decay is following the same equation we had for population growth, just in opposite direction. We understand that when something decays, the mass of this element is becoming like smaller, and we are going to get two new elements. So that's why in our exponent, we are going to have minus r. If my first equation or my first problem was growing exponentially like this, from this value to somewhere here, right? Decay problem is going to have a graph looking like this. So you have initial mass, and then it decreases, decreases, decreases with time. Okay, e to the power of t, that's e to the power of negative t, and that's what we are going to have. Well, usually problem is going to sound like this. For example, we have polony and 210, and somebody gives us half-life of polony. What is half-life? I'm going to explain it. Right now, I'm going to just write down half-life of polony is 140 days. Initial amount of polony is equal 300 milligrams. And they're asking, what is M after 1 year? Typical problem on radioactive decay. Well, first, guys, what is what in the formula actually? Well, M0 is initial population. So somebody gave us initial population, not population, initial mass of the element is 300 milligrams, right? R is a rate of decay, but they did not give us rate of decay, they give us half-life. What is half-life? Well, half-life is time necessary to decay half of the element. What does it mean? Well, we know that M of t, it's initial amount of element, e to the power of negative RT. So in half-life time, this M of t is going to be M0 over 2. So half of the element is going to stay and half is going to decay. Now we can just solve this equation and find out how this half-life or time to decay half of the element is going to change or kind of be related to our rate of decay. Well, what we have, M0 over 2 equals M0 E minus R by T1/2. And this is like half lifetime. Okay. So because M0 is same on both sides, we're going to cancel it and have 1/2 equals e to the power of negative r T1/2. Because exponential function is just by itself, I'm going to take ln of both sides, ln here, ln here. Here ln is going to stay, and I'm going to get ln of 1/2, and here ln and the e going to cancel, and I have r, sorry, T1/2. Now, I'm going to calculate r because actually I know this and kind of can calculate this. So I'm going to have r equals minus ln of 1/2 divided over T1/2. Formula looks so very ugly, right? But we remember that 1/2 is actually 2 to the negative 1. So I'm going to modify this 2 to the negative 1 over T1/2. And this negative 1 can be taken outside. And minus are going to give us plus, and the formula is going to look a little bit less complicated, right? So the rate of decay in our case going to be just ln of 2 divided over T1/2. So in this case, we just can use numbers given in the problem and calculate it. Okay, guys, now we just kind of maybe write it down as a formula, guys. So relative rate of decay R equals ln of 2 over 1 half-life time. And in our case, because we do know half-life, it's 140 days. We are going to have rate equals ln of 2 over 140. Now we're just going to substitute, right? Everything in the formula. So mass after t days, it's m0, which is in our case 300, right? E to the power of negative ln of 2 over 140. That's a rate by time. That's how my mass is going to depend on time. They're asking a question, what is going to be the mass after 1 year? We know that 1 year in days is 365 days approximately. Why do I use days? Because my half-life was given in days, means that the rate R is in 1 over day. That's a unit. So the time is going to be then in days because time sits on the top. Well, so mass of 365 days is equal 300 e to the power of negative ln of 2, 365 instead of t over 140. And we just need to calculate everything. Plug into calculator, and I did this, and my mass comes out as 49.2, well, I don't know, approximately 49.2 milligrams. Why it's milligrams? Because initial mass M0 over here was given in milligrams. Okay, let me label 140 is T1/2 given in days. Well, that's how we solve the decay problems. They look very, very similar to our continuously compounded interest problems. Just the difference is minus. Minus happens because amount of material decreases. With bacteria, amount of bacteria increases. Here, it decreases. Okay. I think that's all. Try to solve at least one problem on each population growth and population decay, which is kind of this radioactive decay or any other decay, actually. Okay, and we are going to finish at this point.